Hello and welcome to our first installment of Semester 2. This is Chapter 9, and we'll be dealing with sampling distributions. We start off with a few vocabulary terms, parameter and statistic. Now, you've dealt with these, you just didn't really know what they were called or what the difference was, so in this chapter we start to talk about the differences between the two. So a parameter is a number that describes the population. This value is often not known because we cannot examine the entire population. Then you have a statistic, all right, which is the name of the class, but it is a number that can be computed from the sample data. It is used to estimate an unknown parameter. So we use a little quick acronym, PPSS, which basically says the population is described by the parameter, okay, and the sample is described by the statistic. Okay, so even though the class is called statistics, and we do a lot of statistics, it's actually the definition of the number that you get from a sample. So when I give you a bunch of numbers and tell you to type them in your calculator, you're actually getting me a statistic. A parameter describes the entire population. And we'll get in much more to the difference between the two. So here's an example, all right, of statistic versus parameter for a mean problem. So the mean income of the sample of households contacted by the current population survey was X bar equals 60,528. Now, that sample, all right, because 60,528 was calculated from the sample, then it is technically called a statistic. So if you went around your neighborhood and went up to people's houses and knocked on their doors and asked them how much money they make, and then you type those numbers in your calculator, and you get the average and you get X bar, that should look familiar, that's a statistic. Now, the parameter is actually the mean income of all 113 million U.S. households. Right? And often that's almost impossible to calculate because you need to survey all of them. So we use samples to help kind of predict for the population. So we have some new symbols that you will recognize both of these symbols, and I've often had people ask me the difference between the two, and now I am telling you. So if the mean is the population, you're going to use mu. And that's what we used when we did a lot of the normal calculations, because you're assuming that that mean is for the population. Now the mean of a sample, so if I give you some numbers and you type them in your calculator, and your calculator gives you X bar, and we know that is the mean. So X bar is actually the mean of a sample, and mu is the mean of a population. Now, when if I do a bunch of samples, if I take samples, you know, if each one of you went out and surveyed 25 houses and asked their income, you'd all get back some slightly different numbers. So we call that sampling variability, and that's the value of a statistic varies in repeated random sampling. Because you're not always going to get the same mean every 25 houses that you go ask. All right, so not only are there mean problems, but there are proportion problems. So here's an example of a proportion problem. The Gallup poll asked a random sample of 515 U.S. adults whether they believe in ghosts. 160 responded yes. So the proportion of the sample who say they believe in ghosts is 160 out of 515, which is 0.31. So it's about 31% of my sample say that they believe in ghosts. So because that number was calculated from the sample, it is a statistic. Okay, so 0.31 is a statistic, and we're going to use that to estimate our parameter of interest, the population of all, or the proportion of all U.S. adults who believe in ghosts. So of course we have symbols for this as well. So we have symbols for mean problems and we have symbols for proportion problems. Now if the population proportion is the actual proportion, you're going to use a lowercase p. And if it's the sample proportion that is used to predict p, you're going to use p hat. Now we should recognize the hat from the linear regression problems. So there it is. There's the p with the hat on it. All right, so there's our new symbols. Now, a couple of other things. We talked about the sampling variability. when you did the activity in class, every time you calculated the mean, everybody was a little bit different. So we want to know what happens if we repeated that process a lot of times. So we're going to take a large number of samples from the same population. Each sample that we take, we're going to calculate the sample mean, x bar, or the sample proportion, p hat, for each sample. And then we're going to make a histogram of all those values, which again you did in class on the board. And then we're going to examine the distribution displayed in the histogram for shape, center, and spread, as well as outliers or other deviations. Once we do that, that histogram of all possible samples is actually called a sampling distribution. Of a statistic is a distribution of values taken by the statistic in all possible samples of the same size from the same population. So here's a visual of what we did in class. I gave you this applet, and you have your population data here, right? The parent population. So this is approximately normal, and then we're going to randomly pick values out of here, okay, using a simple random sample technically, and we're going to average those numbers, and then we're going to plot them on the graph. So I'm going to start off with a mean of 2, and I'm going to animate it so you can see what's going on again. It's randomly selecting 2 numbers, it's averaging them, and plotting on the graph. We do that again. Okay, you see that varies. I got 2 completely different numbers, different average. I do that again. I do that again. All right, I'm going to repeat this process a lot of times. I can use the software to help me out. I can do it 5 times at a time. And you start to see this graph, this histogram growing. All right, and it starts to take shape. Okay, and to speed it up, I'll do 1,000. Now you get a much better idea of what that would look like if I did it repeatedly. All right, it starts to take on a kind of symmetric, approximately normal shape. Now I'm going to click 10,000. So what you should notice here is the mean of this is 15.97. Well, the mean of the original graph was 16, so that's pretty close. So if I repeated this process a lot, I would get a mean pretty close to what the mean of the parent population is. Now, for comparison purposes, let's look at what happens if I increase this to 25. So I'll animate 1. It draws 2. Now, I'm going to pick 25 out of here, average those, and plot them down here. And again, I'm going to repeat that process thousands and thousands of times, and I see what happens here. So when my sample size was only 2, there's a lot more variation in this graph. It has a much bigger standard deviation, 3.53. When I pick 25 at a time, there's not as much variation. The spread of this graph, it's not as spread out. It only has a standard deviation of 0.9. You can see the most numbers were right on the mean. So there's not as much variation if I increase the sample size. And that's a big concept that we will be talking about. Okay, the variability of a statistic, kind of what I was just looking at, described by the spread of the sampling distribution. Spread is, the range, kind of, how spread out are the data, is the standard deviation. Larger samples provide smaller spread. There's less variability in larger samples. They produce an estimate close to the true value of the parameter. Okay, same thing here. The mean was 16, all right, but this is less spread out than if the sample size was 2. As long as the population is much larger than the sample, say 10 times, the spread of the sampling distribution is approximately the same for any population size. Okay? Now, let's move on to some examples of determining whether it's a mean or proportion, and determining which is the parameter and which is the statistic, and we'll use proper notation. So you may need to pause it periodically to kind of copy these questions down, but these are the types of questions you'll be dealing with in class. So the candy company claims that 10% of the M&Ms it produces are green. You buy a bag of M&Ms and find that there are 25% green. So first off, I'm going to identify this as a proportion problem. And I know that mainly because I'm dealing with percentages. Now, that's not always the case, but for the most part, because I'm dealing with percentages, this becomes a proportion problem. So the 10% of the M&Ms that it produces are green, that's of all M&Ms. So that's actually the parameter, because that number represents the population. So that would be P equals 0.10. Now, 25% comes from a bag of M&Ms that I bought. So that's kind of like my sample, and that's the statistic. and therefore p hat equals 0.25. All right. Now, next problem. A college's data about the incoming freshmen indicates that the mean, that's a hint, of their high school GPA was about 3.4. You ask 25 students in your stat class for their high school GPA and find the average to be 2.8. So this is a mean problem. Okay, we are dealing with quantitative data, and the numbers are 3.4 and 2.8. 3.4 is a population of all incoming freshmen. So that's the parameter in this case. And it's P equals 3, I'm sorry, not P. Mu equals 3.4. Mu is the mean of the population. I asked 25 students, so that's a sample. That's a piece of the population. And I get an X bar of 2.8. Okay, problem number 3. The weight of potato chips in a medium-sized bag is stated to be 10 ounces. You buy a bag of Lay's and weigh 8 ounces of potato chips. Okay, now, again, I'm dealing with quantitative data, so that is a mean problem. All right, numbers that I can average. The parameter in this case is the population. So Lay's claims that all of their bags contain 10 ounces on average, so that's a mean. Mean is 10 ounces. And you buy a bag of Lay's, so that's kind of like your sample. So the statistic in this case, X bar, is 8 ounces. All right. And the last problem, state police believe that 70% of the drivers traveling on a major interstate highway exceed the speed limit. They plan to set a radar trap and check the speed of 80 cars. They find that 60 are speeding. So here we're dealing with percentages. So this is a proportion problem. All right. And again, it's categorical data or qualitative data. You fit in a category of either speeding or not speeding. So the parameter, all right, is the true percent that are speeding, and that's 70%. All right. Now, out of the 80 cars, that's a sample. We find that 60 are speeding. So because that's from the sample, that's a statistic. And we get P hat equals 60 out of 80, which is 0.75.